Dear participants, good morning. It's my pleasure to announce that the third International Conference on Design, Simulation, Manufacturing, the Innovation Exchange is opened, despite any other problems in the global world. This year has become a real challenge to all of us to organize conference in a principally new format. And in my opinion, we have successfully solved it. And thank you very much to all team members, to all participants for your contribution and patience. I would like to give a brief overview about DSMIE conference series. Our history starts in 2018 in SUMI. We found that conference which unites researchers from such areas as design, simulation, and manufacturing is urgently needed. Now, DSMIE conferences is the international forum for fundamental and applied research and industrial applications in engineering. The conference focuses on a broad range of research challenges in the field of manufacturing, materials, mechanical, and chemical engineering, addressing current and future trends in design approaches, simulation techniques, computer-aided systems, software development, ICT tools, and Industry 4.0 strategy implementation for engineering tasks solving. The conference is organized by SUMI State University, National Technical University Kharkiv Polytechnic Institute, and International Association for Technological Development and Innovations. In partnership with Technical University of Košice from Slovak Republic, Kelsey University of Technology and Poznan University of Technology from Poland, University of West Bohemia from Czech Republic, Association for Promoting Innovative Technologies from Croatia, as well as Springer, EasyChair, and Strike Plagiarism companies. Our vision is based on three fundamental principles. The first one implies teamwork for the promotion and popularization of science, technology, engineering, education. The second one describes the main mission of the conference, discussion and ideas exchange. The third principle certifies that we have to publish cutting-edge research results. Our library is expanding. Now you can see 4 books. Our previous books are indexed by Scopus and Web of Science core collection. We are working on adding this year's books to the Web of Science core collection too. I would like to thank members of the program committee and invited external reviewers for their efforts and expertise in contributing to reviewing, without which it would be impossible to maintain the high standards of peer-reviewed papers. They devoted their time, energy for peer-reviewing manuscripts. Our reviewers come from all over the world and represent 29 countries and affiliated with 63 institutions. Thank you very much to all of you. I would like to pay attention to the participants that extended versions of your research can be published in our partner journals using a fast-track option. These journals are Management and Production Engineering Review, Archives of Mechanical Technology and Materials, Journal of Engineering Sciences, and Advances in Thermal Processes and Energy Transformation. Thank you very much to keynote speakers Erwin Rauch from Italy, Dagmar Tsaganova and Ladislav Morovic from Slovak Republic, Mateusz Barszewski from Poland, Arun Nagaraja from Germany, and Alex Enrich Prast from Sweden, for sharing their knowledge and experience. Thank you very much. This year we received contributions from 28 countries around the world. Through peer review process, the program committee accepted 93 papers written by authors from 23 countries. Thank you very much to authors for their contribution. The acceptance rate is about 58%. The internationalization rate is about 37%. The books from previous editions have achieved 150 citations. The comprehensive analysis evidences that not all papers contribute to the indicators. The list of top 5 the most cited papers is presented at the slide. They made 31% of citations from published papers for 2 years. A similar analysis was carried out regarding visibility issues. These data are important for us while planning the next editions for the conference, particular subtopics. Thank you very much to DSMIE team. Their involvement and hard work were crucial to the success of the conference. And our motto is, together we can do more for science, technology, engineering, and education. I wish all participants fruitful work, and let's enjoy the conference together. Let me introduce now our co-chairs of the conference, Professor Andriy Marchenko, Vice Rector for Research Work, Acting Rector of National Technical University, Kharkiv Polytechnic Institute, with invitation to participants from Kharkiv.
Шановні колеги, від імені харківських політехніків щиро вітаю учасників конференції наукової міжнародної DSMIE-2020 з її початком. Ця конференція була започаткована Сумським університетом і сьогодні крокує по університетам України. Ми вдячні нашим партнерам за те, що ми зробили таку велику роботу, зробили підготовку до проведення цієї конференції. Для нас це дуже важливо і почесно. Важливо, тому що в цьому році ми відзначаємо, наш університет, Харківський політехнічний інститут, відзначає своє 135-річчя. За годи історії, безумовно, в університеті склалися наукові школи, наукові традиції. В тому числі, я би сказав, може, в першу чергу, це механіки, інженерія, матеріалознавство, які дали для розвитку економіки дуже багато інновацій. Серед цих інновацій я хотів би сказати таку відому інновацію, як танк Т-34, який був створений випускниками і вченими нашого університету. За визнанням Уінстона Черчилля в 1945 році, він сказав, що цей танк є кращим танком Другої світової війни. За визнанням сучасного рейтингу Discovery, він визнаний як кращий танк всіх часів бронетехніки. Ми знаходимося біля ротора турбіни виробництва Харківського турбінного заводу. Цей ротор є видатним досягненням механіків, тому що цей ротор визначає світовий рівень. Ми часто кажемо, на світовому рівні до багатьох виробів, які виробляються. А до цього ротору можна сказати, що він визначає світовий рівень і він за своїми показниками кращий за всі відомі аналоги. Безумовно, механіка, машинобудування, інженерія – це дуже важливий аспект розвитку цивілізації. І якраз цим питанням буде присвячена конференція, яка проводиться. Я бажаю всім учасникам конференції наснаги, я бажаю всім учасникам конференції нових знайомств, нових ідей і нових рішень. І я певен в тому, що ця конференція пройде успішно, і запорукою такого мого висновку є та попередня робота, яку ми виконали з партнерами, і та активність, яка була заявлена учасниками конференції. Дякую.
Щиро вітаю всіх учасників з початком роботи нашої конференції. Це третя конференція, тобто можна вже зазначати, що вона традиційна. Так, вона проходить в незвичних умовах, в умовах епідемії коронавірусу, тому спілкування, всі доповіді будуть в дистанційному режимі, але ми і наш університет, і всі наші партнери достатньо високооснащені, високотехнологічні, і ці технології зайшли вже давно в наше життя, ми ними постійно користуємось, тому у мене є впевненість, що зміна формату, вона не вплине на суть, а можливо ще і додасть чогось позитивного. Ми щиро вітаємо і вдячні нашим партнерам, співорганізаторам конференції, Харківській політехніці, з якою у нас давні стосунки, сумісний історичний шлях, сумісні проєкти. Ми вдячні і нашим партнерам Міжнародної асоціації технологічного розвитку і інновацій. Вітаю наших колег, партнерів із університетів Польщі, Чехії, Словаччини, Хорватії. Всього в конференції приймає участь біля 300 науковців, які представляють більше 100 організацій, університетів із 23 країн. Переважним чином це європейські країни, а також є представництво і Сполучених Штатів Америки, Японії та інших країн. Щиро вітаю наших спікерів. Це відомі науковці, які мають авторитет в науковій сфері, мають достатньо значущі індекси гірше і представляють дружні нам університети, які входять до топ-груп таких відомих рейтингів, як QS, Times Higher Education, Шанхайський рейтинг та інші. І навіть і це додає впевненості в тому, що конференція буде успішною. Всім наснаги, творчих успіхів, здоров'я. Хай нам всім щастить.
Yeah, I would like to pay attention to the slide now. This is an agenda of our conference for today. We will start. Slide, please. Next one. Next one. Yes, as you can see, now according to our agenda is keynote session number 1, and I would like to introduce our keynote session chair, Professor Olaf Ciszak from Poznan University of Technology. He is a very experienced expert. He was the first keynote speaker during our first conference in Sumy. He also was a session chair during the second conference, and I would like to give him the chair rights. Olaf? Turn on your microphone, please.
Sorry. Do you hear me? Everything is okay?
Yes.
Yes, thank you. Thank you, Vitaly. Thank you, dear rectors. Hello, my dear society from the DSMA. In this year on the internet, we connected with our discussion sessions. I'm very happy and honored to me to provide the first session, Keynote Session. My dears, at the first, I would like to present our plan. We have the three very important keynote speeches. The first will be Professor Edwin Rausch is present. Okay. The second will be Professor Dagmar Caganova is present. I don't see her. And
he will join us.
Yes, okay.
Join.
And third, Speech will be from Professor Mateusz Baczewski from our university, from Poznań. I see Mateusz, hello. But at the first, I would like to say a few words about Professor Erwin Rausch. He received his Bachelor of Science in Logistics and Production Engineering from the Free University in Bolzano. He also holds a Master of Science in Mechanical Engineering from the Technical University Minsk and the Master of Science in Business Administration from the Business School TUM. Professor Dr. Rausch obtained his PhD degree in the Mechanical Engineering from the University of Stuttgart with summa cum laude. Currently, he is an assistant professor for manufacturing technology and system at the Free University of Bolzano. His current research is on Industry 4, smart and sustainable production system, digitization and assistance systems in production and axiomatic design. Also, he is the head of the Smart Mini Factory Laboratory for the Industry 4 and the Free University of Bolzano. As a project manager, he coordinates the European Union research project SMA4 Industry 4 for the small medium enterprises. Working with research partners from Europe, the United States and Asia. He was a visiting researcher and professor at Chiang-Mai University and Worcester Polytechnic Institute in the United States. His speech title is Industry 4+, the next level of intelligent and self-optimizing factories. Dear professor, the internet, the YouTube, the Skype is yours. Please, you can start.
Thank you very much, Professor Zizak, for the very nice introduction. And thank you also to the conference team, to the conference chair, also to Professor to Vitali for inviting me to this keynote speech. So I want to present you now what is my understanding of a next level of Industry 4.0 going towards intelligent and self-optimizing systems. So you see also this title, Industry 4.0 Plus. Afterwards, I will discuss with you also what I mean with this plus or with this next level of Industry 4.0. Next slide, please. So to give you an overview of the structure of the presentation, at the beginning, I want to present myself and to introduce also what is my research in the Free University of Bolzano in Italy. And afterwards, I will do with you a journey back in the past of Industry 4.0 to see what are the aims or what were the original aims of Industry 4.0. What will be also the future in this field? And this brings us then to the third section where we will speak then about this next level of Industry 4.0 or this Industry 4.0 Plus. So next slide, please. So now I don't see anymore the slide, but I think maybe on the YouTube you can see the next slide. So it's about a short introduction about me, but I would skip that slide as we already had the very nice introduction by Professor Zizak, and therefore the only thing that I can add maybe also on that side is that in this project where I'm working with different universities from Europe, from the United States, as well as also from Asia on the topic Industry 4.0 for the smaller companies, for the SMEs. We work together also with the Technical University of Košice, with Professor Vladimir Modrak and Professor Jan Pitel. And I know that Professor Jan Pitel is also a member of the program of this conference, therefore greetings also to him and to his team. So next slide, please. Short overview also about our university so that you know also where I'm from. I'm from Italy, but in the very north of Italy, where we are in at the border between the German culture and the Italian culture. Bolzano is a special place because we have there people that are speaking German, people that are speaking Italian. We are a quite young university. We are funded in 1997, We are a small university with 4,000 now 500 students, but we have a very international profile from teaching staff and as well as also from students. We are #1 among the smaller universities in Italy and also among the 10 best small universities worldwide, according to the Times Higher Education rating. And at this university, I'm working in the research group Industrial Engineering and Automation, and I'm representing there the topic production and supply chain management. So next slide, please. I'm heading also the Smart Manufacturing Laboratory. It's a learning factory lab that we started already in 2012 with doing lean production, and then in the following years with the start of Industry 4.0, we changed towards Industry 4.0, and basically this laboratory works on teaching, of course, therefore teaching in a practical environment. Therefore, we have not small toy robots, but we have a real industrial environment with a real production line where we produce pneumatic cylinders as a simulation project with students, as well as also with people from industry. So we are also working and qualifying people from industry in Industry 4.0. And of course, we are doing also research, basic research, applied research in order to go ahead also in the direction of bringing Industry 4.0 to the companies, and we have a certain focus there also on the smaller companies. This we can see also on the next slide. So here you see an overview about the research fields that I am working on in this laboratory. So all is about SME 4.0, how we can introduce Industry 4.0 in the smaller enterprises. We defined there 3 research fields. One is how to integrate the human in manufacturing, which is a really important and quite tough topic. The other one is technology. What kind of technologies can help us to do this? And the other one is organization, where we look how we can change the organization behind and how we can digitize also smaller and industrialized companies. So if we go now to the next slide, we see the first research fields on human and what are the topics where we are working there. The first topic is human-centered production, where we work on the topic Operator 4.0. What will be the new role of employees in Industry 4.0? What could be new professions or new job profiles also with Industry 4.0? For example, we had in the past a lean engineer. In the future, maybe we have a production data analyst or something similar. A second topic we are working on is sustainability, but not the ecological and not the economic side of sustainability, but we are looking more on the social side. So what are the new forms or models of work 4.0? How we can integrate also maybe weaker disadvantaged groups like older employees or disabled employees by providing the right assistance systems or by providing the right workplaces. And the third topic is about qualification in Industry 4.0, which is something really important for us as academics and universities to qualify not only our students, but to have a look also towards industry, teaching also the professionals that are working in industrial companies in order to increase also their competences in this Industry 4.0 technologies. Next slide, please. So the other research field I'm working on is technology. And here we speak first about digital factory, virtual planning systems. So what are the typical systems that you can use to create digital twins or to realize a cyber-physical production system, how to use also systems from virtual reality or augmented reality in manufacturing. Another topic is worker assistance systems in production. You see here a picture of how to project work instructions on the work table and therefore facilitating also the learning curve or a ramp up of a new production line and to assist the operator doing his work. Another third technological topic is intelligent human-machine collaboration, where we did a lot of research and activities in the last years on collaborative robotics, because we see the big potential also for the smaller companies, so that they can introduce a flexible automation also with smaller lot sizes. And here we are now combining this collaborative robotics with artificial intelligence, studying also what can be the psychological effects regarding the acceptance of the systems for the operator. So next slide, please. The last research field is organization, and here we have this one of the first large EU project on Industry 4.0 that goes towards smaller companies, which is this SME 4.0, where we developed an assessment tool for Industry 4.0, where we are already developing a readiness model, and we are discussing a lot also sustainability and ethics, and what's the matter of ethics also when we introduce Industry 4.0. In the second topic, we try to digitalize the companies, going from the top down, therefore from the ERP system to the machine level, having a vertical data integration. We developed with a starter company also a digital shop floor management system, and work on smart data analytics using also machine learning in manufacturing. And then we have also design of complex systems, where we try already to use axiomatic design, biological transformation, and artificial intelligence as methods and technologies to approach complex systems and to find solutions there. So this was a rough overview and presentation of what I'm doing and how our research group is structured and how our laboratory is structured. Now in the next slide, we can see that we go now towards the aims of Industry 4.0. And if we go another slide forward, we can. So next slide, please. Yes, the next one. Thank you. And here we can see a picture of going into the past, a picture of the Hanover Fair in 2011. And you see there also three really important persons for Industry 4.0, therefore Kagermann, Lucas, and Balster, the three representatives of politics, of business, as well as of science, that proclamated the first time Industry 4.0 at this Hanover Fair in 2011. And we can see also some of the objectives or the aims that they proclamated, like having cyber physical systems to bridge this real world with the virtual world, to have intelligence, to have autonomous decision making, to aggregate information in connected systems, where we have connected factories where the smart product communicates with the operator, with the machines, as well as also with the production environment. This means with customers as well as also suppliers. And with the final aim to have a self-optimization, self-reconfiguration, and self-diagnosis of our factories. So this was a big step into the past, where we see what was the beginning of Industry 4.0. So now we are in 2020. This means that we had already a story of nearly 10 years. So if we go to the next slide, I want to take you also to a short journey of what happened there in Industry 4.0 over the last 10 years. So if we click now once on the slides, then we see that the term Industry 4.0 has been founded in 2011 at the Hanover Fair. If we click another time on these slides, then we see that from 2011 until 2013, we had the Industry for Zero working group in Germany, led by the Architect Group, that worked on a new strategy, a high-tech strategy for Germany based on the concepts of Industry for Zero. And if we click another time, then we see that in 2013, this working group came up with a final report for the German ministry and delivered this report, and then the German ministry started with this strategy for introducing these technologies in industry. Clicking another time on the slides. So I don't see the slide, therefore I cannot check if you see the right things, but I hope you see now also that from 2013 to 2015, there were the first conferences also where the term Industry for Zero was then brought onto an international level. And this was then also the starting point where we had the start of research activities on Industry for Zero, and where this term was spread then over the world. For example, in USA, we speak there more about IoT or smart manufacturing. In Canada, they are speaking more about intelligent manufacturing. In Asia, it's more the term Industry for Zero that it's describing. That's what we mean in Europe with Industry for Zero, but it's always the same things. And in the time from 2014 until 2017, we used several times to clarify also what is Industry for Zero and what are the right technologies for that. Afterwards, 2015 to 2018, most of the European companies came out with national plans for implementing this Industry for Zero in the companies. In Italy, for example, we started in 2016 with the National Plan for Industry for Zero, giving also incentives to the companies introducing new technologies. If we go then once ahead in the slides, we see that other industry, non-industrial sectors tried also to use digitalization, like service industry, but because it's not an industrialized sector, they used more than the term digital transformation, which is now a synonym also for Industry for Zero in these non-industrial sectors. In 2017, we started with our European project on smaller companies. Therefore, here we have an increase also in publications regarding the implementation in SMEs. And if we go then once ahead on the slides, we see what's happened afterwards in the years after 2018. So please click once on this slide. Yeah. Thank you. And here we see that most of the European countries have now installed or implemented in a certain way competence centers that they demonstrate also successful pilot projects in order to increase the acceptance by the companies as well as also by the employees. In the meantime, also cities and regions try to do digitalization. And also the universities have seen this trend towards Industry for Zero. They reacted to this, and they started also with engineering education for zero programs, therefore to adjust the existing study courses, study programs, and to introduce in the study programs more content of Industry for Zero related topics. And if we go once further on the slide, we see what is now the present, or what will be also then the future in Industry for Zero. And here a lot of people are speaking also about artificial intelligence, which is the new hype with machine learning, deep learning. We want to use this technology now in manufacturing. And it's also something that we can find in the new strategies like Digital Made in Germany or Made in China 2025, where China proclamates to aim of being the leader in artificial intelligence until 2025. In addition, we can find it as a major goal also in the new program of Horizon Europe, together with the goal of sustainability. So artificial intelligence, of course, is something that will will where we will work on also in the next years and also in the future. And this brings us then to the next slide, asking us what is now the future? Therefore, what's next? Was this now the end of Industry 4.0? Is it now time for something new, for a new industrial revolution? What's the next level? And here we see that there are also some concepts according to Society 5.0, which is a concept that was introduced already in 2016 by the Japanese Business Federation, this Keidan. And I want to explain here that this is a really important revolution, but it's not an industrial revolution as somebody also explains, because it's a revolution that happens in society. Therefore, in people, it affects people's lives. So we were going in these steps to Society 5.0, starting from the hunting society, going over then to the agrarian society. Then we had this really important two industrial revolutions with mechanization, electrification, that helped us to achieve a level of an industrialized society, therefore this Society 3.0. Afterwards, the computerization, electronics brought us to the information society, and now the fourth industrial revolution with internet connectivity, with all the technologies to bring together the cyber world with the real world of human-robot collaboration and so on. This now brings us towards to this super smart society, therefore this Society 5.0. So Society 5.0 is not substituting Industry 4.0, but it's something where we see that the results of Industry 4.0 are going now to affect people's life in this concept of Society 5.0. And now if we go on the next slide, we see another term that is circulating. If we look at the future, so what's next? So it's also quite easy. If there's an Industry 4.0, maybe there could also be of Industry 5.0, but is it the case? Because if we look at the definition of this Industry 5.0, taking a look to some papers from literature, we see that people speak there about cyber-physical systems, about intelligent systems, about connectivity, high-speed internet, about collaborative robots, about fast decision-making. But I want to state this question: are these not the goals of Industry 4.0? Therefore, is this not something what we already do in research and what we will do also in the future? So going to the next slide, we see there an overview of what are the objectives of Industry 4.0 if we take out this Acatec report from 2013. And we can see there that we already have achieved, or we are on a good level in several of this target or this objectives that were stated at this time. Therefore, cyber-physical systems, the horizontal vertical data integration, to have RFID and smart products, to have connected factories. I would say that it's perhaps not completely achieved in all the levels of industry, but we are on a really good way in these concepts. There are other aims that are also described in this report, which are intelligent manufacturing, which is self-regulation, self-optimization of manufacturing through intelligent systems, as well as also autonomous systems and self-organizing value chains. And this are, of course, topics where we still need research to fully implement all the original objectives of Industry 4.0 that were stated in 2011 and 2013 by the Acatec group and also by other scientists of that time. So this let me come to the next slide, where we go then also to see what is the next level of Industry 4.0 according to my opinion. So according to my opinion, we have not a completely new industrial revolution, but it's a certain second phase or second level that we want to achieve now to fulfill all the objectives that were already stated in the past nearly 10 years ago. So now let's see what I mean with this. Going to the next slide. You may know this picture, the typical picture of the fourth industrial revolution. And I don't speak about the first three industrial revolution. You know that picture already. I want to focus more on the right side of that picture, where we had in the last 10 years technology-driven era, where we worked on digitalization, industry, Internet of Things, advanced technologies. We achieved this smart factory. But in the future, we will need to implement much more data and intelligence-driven innovation. And therefore, this will be the time for artificial intelligence. This will also be the time for biointelligence. In order to, at the end, fulfill this original objective of Industry 4.0 stated in 2011 to become an intelligent and self-optimizing factory. So reassuming, we have now in the present all the technical requirements for data collection and data management. Now the next step is to make sense of this data. Next slide, please. Here we see now what I mean with a smart factory, with an intelligent factory. Smart factory is a manufacturing system capable to apply previously acquired knowledge. Therefore, we are now able to collect a large amount of high quality data. We have all the sensors and technologies. We have also the software systems for a seamless data exchange. We have also cloud technologies to store and manage data. And we have big data analytics also to process data in a more structured data. But what's missing is to have intelligence in our factories. Therefore, if we click again, we see at the right side then the definition of what I mean with an intelligent factory is a manufacturing system which is able to autonomously acquire new knowledge and to apply it for this purpose of self-optimization. Therefore, taking advantage of the data that we were able to create in the last years, use now the new tools of artificial intelligence to learn from nature, therefore to use also biological transformation, and something that is more a challenge for us as universities or also the high schools and so on, to qualify also then the people in this regard, therefore to qualify people to use data and to implement also these things in our factories. So going to the next slide, a rough overview of what I mean with this first level of Industry 4.0. Maybe you know this picture also in different other forms. This is, for example, taken from this national plan of Industry 4.0 in Italy, where in the last years, the Italian government financed also investments in these technologies like collaborative robotics, adaptive manufacturing, augmented reality, cloud, big data analytics, and so on. Therefore, these are all the things that we already have as technologies, and that are the basic requirements also then for the next steps in order to use then this data and to use it for optimization. So that if we go now one slide ahead, we see this next level of data intelligence driven innovation, where I want to speak mainly about these two things. Therefore, one is the artificial intelligence, the other one is the biological intelligence. In the artificial intelligence, you know, we speak there about machine learning, deep learning, neural networks, and so on. Therefore, engineers have to work a lot together with computer science. If we take a look to the other side, to biointelligence, here we talk about biological systems, about molecules, about cells, about organs, what we can learn from the ecosystems in biology, how we can transfer this knowledge to our manufacturing systems in order to take advantage then for our manufacturing systems. And this means that we have to collaborate with our colleagues from biology, from biotech. And here, one of the big challenges for the future will therefore be how to bring together all these colleagues, therefore the engineers, computer science and biology, in order to achieve here the best solutions. For example, in our university, our rector follows a really smart strategy now, bringing together the faculties of engineering and computer science in one single faculty in order to strengthen also this collaboration between these two disciplines. And the next step would then also be to work on this other part on biology, how to introduce also this and to enhance also collaboration on that. So to give you then also some examples, if we go to the next slide, talking about artificial intelligence, what are here the opportunities? So please, one slide ahead. Thank you. So artificial intelligence is something that we already have since several years, but now is the right time to use these algorithms also in manufacturing, because now we have the computational power, we have the hardware, we have now the technological prerequisites. Therefore, we have the technologies where we can use the artificial intelligence. That will be one of the next opportunities. You see that picture on the right side also. We have the collaborative robots that are simulating our arms, therefore simulating the action. We have the perception of the robot with the sensors integrated in the joints. We have the perception by having sensing systems, as you see here, this device from Smart Robots. That what we need to develop for the future is that we need to teach these devices how to think alone. Therefore, how to integrate here intelligence in these devices. Going to the next slide. We see here some fields of future application. Therefore, one is, of course, human-robot interaction. You see here also a video of a laboratory setup in our Smart Manufacturing Lab, where we set up a collaborative robotic workstation. We introduced computer vision and machine learning algorithm for object recognition and motion recognition. We used the AI algorithm for action planning and try to predict operators' intention, and therefore to use this also to reduce idle time and to optimize the efficiency of such workplaces. Other fields of application can be automated quality checks, predictive maintenance, as well as also engineering design. So next slide, please.
Dear Professor, 2 minutes.
I know.
Okay?
Yep.
Thanks.
I'm running. And here, regarding the biointelligence and biological transformation in manufacturing, we see two pictures. One is from Bern in 2018, the other one from Mia, therefore Fraunhofer 2020. We see that here basically we can have two ways. One is the technology push, therefore going out from a technical problem, looking into nature and looking for solutions. The other way is to start from natural or biological phenomena and to see where such phenomena could have a positive effect or impact also on technical systems. So these are the typical ways how to deal with biological transformation, where we have then also 3 levels. The one is bio-inspired, where we get inspiration from biology, and the other one is integration, where we use biological systems in technical systems, maybe bacteria or microorganisms in production processes. And the third level is the interaction, therefore having biointelligent manufacturing by combining technical systems with biology, with computer science, and therefore information system. And this is now something really important where we have to work in the next years. Next slide, please. And here, one example, also a picture there from this Fraunhofer report about future fields of application for bio-inspired materials, bio-inspired data processes, bio-inspired workplaces. And here one picture regarding biocompatible man-machine interfaces. Maybe in the future we have such biocompatible magnetic skins for controlling devices, for controlling robots or other things. So these are future fields of applications also for this biointelligence. And with the next slide, I want also to conclude the speech and to summarize what we have heard. So the last 10 years were mainly technology driven. The next, I don't know if it's then other 10 years or more or less, but the next future will be much more data and intelligence driven. We have not yet achieved the original goals of Industry 4.0. Therefore, in my opinion, we are not speaking about the Industry 5.0 or some other new industrial revolutions, but it's still Industry 4.0, but we are going now towards the next level of it. And what will help us in the future to achieve this goal of intelligent and self-optimizing factories will be to go towards artificial intelligence and biointelligence. And this is also why I chose this topic as a keynote speech here, because I want also to motivate and to motivate other researchers to do research in this regard, therefore to follow also this way of biointelligence and artificial intelligence. Thank you very much. And if there are any questions, I'm available.
Dear Professor, thank you very much for your interesting speech, very interesting for me. Maybe some questions. I look on the YouTube, on some chat questions. I don't see any question. Maybe from our society, from the internet. Maybe one a little bit question, because at this time we have a very tired time with the pandemic. What do you think? How we should start with the continuum of Industry 4 and with the future to Industry 4+ or 5.0? Because a lot of our enterprises, small, medium, and highest, have some problems with economic and with another partners collaboration. With the, I see at this moment some pausa time, something like this. What do you think about today's?
Yeah, we have noticed the same, that because we wanted to start some industry projects also in January, February, and afterwards, of course, with the pandemic situation that we had, everything was blocked, and we are now reactivating this contact because we see that now the most stressful time is over for the companies. They can again go to bring their worker into the companies, to work in the companies and to restart. But of course, it's not the same as before. So something where we prepare now also our companies is for this restart. Therefore, yes, automating, it's also a big time for automation, because you have to work in situations where you cannot work anymore with two operators. I know one example of a company where they have to work together because the product is that heavy. And as they are not able to, for legal restrictions, to work together, they are moving now to automated solutions. And here we want to help this company also with a solution with collaborative robotics. Therefore, the robot taking over the heavy load for the operator, in sense of substituting in this sense also the second operator. But they are able then to go on with the work of this product. And in a next step, of course, a big issue will also be to reactivate local production networks, which has also become quite important in this time. Therefore, being able also to find local suppliers, to have resilient and local supply chains, therefore to secure also that the procurement, the purchasing is working, that the distribution of the products is working, and also here instruments from Industry 4.0 can help also to define these platforms for organizing or managing this collaboration or these production networks. So these are two topics where we have seen a lot of activity now also together with the companies.
Thank you very much. I have the same idea of mine. It is very important to collaborate and provide some automation in the industry. Thank you, dear professor. Any question from the chat or from our partners, from the listeners? No, thank you. Thank you, professor.
Thank you.
To the normal time, maybe we can meet on the next conference. Thank you.
It would be very nice.
Thanks. My dears, the next keynote speaker will be our professor Dagmar Caganova. A short introduction. Dagmar Caganova is also the co-founder of the European Alliance for Innovation in the Slovak Republic, management committee member of the ACOST, and the executive committee member in Danube's Academic Consortium, steering committee member of Danube Strategy PA7, Knowledge Society Science, Research Innovation in ICT for Slovak Republic. Her professional interests, research topics and international collaborations are mainly focused on intercultural and innovation management, human resource management, mobility and smart cities, international relationships and gender diversity. She is a member of journal editorial boards, organizer, steering committee member of many national and international summits and conferences. She also acts as a tutor on the PhD study program and has participated in solving national and international scientific and educational projects in various project schemas. At present, she acts as a project lead for MTF in Horizon 2020 project, linking research and innovation for gender equality with acronym CLIPPER. She is a special issue journal editor and co-editor of the books published by Springer Nature and author of scientific monographs, papers in curated content journals indexed by Web of Science and in Scopus. The title of the keynote speech proposed by Professor Caganova is Industry 4, Best Practices and Challenges. Dear Professor, I see you are ready. The internet and the Skype is yours. Please start. The stage is yours.
Thank you very much, Professor Chisak, for introduction. Firstly, I would like to express my sincere thanks and that it's really an honor for me to be part of third international conference on design, simulation, manufacturing, and the innovation exchange. I would like to give this speech together with my colleague, Associate Professor Ladislav Morovic, who comes from the Institute of Production Technologies. I am from the Institute of Industrial Engineering and Management, and we are both from the Slovak University of Technology in Bratislava. Next one, please. The layout of our presentation is we would like to share with you our experience with Industry 4.0 and connection to competencies and also best practices of the project we are solving nowadays. It's a national VEGA project, working competencies in the context of Industry 4.0 development, and H22 projects. One of them is linking research and innovation for gender equality, and also directional composites through manufacturing innovation. Next slide, please. Our university, Slovak University of Technology, is located in Bratislava, and we offer university education and also research in the area of engineering, as well as in arts within Faculty of Architecture. Our history comes 250 years ago to Mining Academy in Banská Štiavnica, and we try to put also serious focus on practical learning methods. And nowadays, I have to say that there is serious and direct collaboration with industrial partners, and we realize that strong international links are crucial. Also, we realized that nowadays in Europe, two aspects are really important, and it's innovation and networking. As you can see in the following slide, Slovakia is rather interesting as she is located in the heart of Europe. And what is maybe relevant fact is that theoretically, within one day, you can visit 5 capitals. You can get from Bratislava to Austria to Vienna within 1 hour something, to get to Hungary, to Budapest within 3.5 hours, or to get to Czech Republic, to Prague within 3.5 hours, or to reach Warsaw 4.5 hours in Poland. Our faculty is located in Trnava, and it is approximately from Bratislava about 30 minutes by highway. Another interesting fact is that our Slovak University of Technology has 6 faculties located directly in our capital, Bratislava, and the only one, our Faculty of Material Science and Technology, is located in Trnava. I see that our university, together with Sami State University, has pretty many things in common. Also faculties like Faculty of Civil Engineering, Mechanical Engineering, Electrical Engineering, Information Technologies, Chemical and Food Technology, and many others have many things in common. And also we have other institutes like Institute of Management and research centers. Next one slide, please. Our faculty of Material Science and Technology, has also several institutes. Institute of Material Science, Production Technologies. Our institute is Institute of Industrial Engineering and Management. And also we have research workplaces, like Centers of Excellence, Center of Excellence of 5-axis machining, or Center of Excellence of Diagnostic Methods. And also we are very proud on University Scientific Park Botova. Next slide, please. We realized that Industry 4.0 is crucial for competitiveness. It's challenging for modern technologies, and we are pretty aware that enterprises are able to increase productivity, efficiency, and certainly stronger customer orientation. But the basis for success are always people, and that's why limitations are connected to human capital. From this is really evident that new business models are demanded, and we need people who have new knowledge and skills, and it is reflected that there is necessity to change the approach in education, what should be reflected in new syllabus. Please, getting to the next slide. We realized that moved from mechanization towards mass production, automation, to cyber-physical systems, and there is rather important Internet of Things and networks. And in Slovakia, we have also CEO Martin Morháč, who is recognized as Industry 4.0, and we are really happy that we have a chance also within our faculty, university and institute to collaborate with them. And his perception of Industry 4.0 is through digitalization and interconnection of information via horizontal integration. And of course, it is necessary to apply engineering in the whole value chain, and it is accelerated via exponential technologies. Competencies within Industry 4.0 are changing. From 2004, the most important, complex problem solving, coordinating with others, people management, and so on. And nowadays, within World Economic Forum, skills and competencies predicted for 2020 is also very strong focus is put on critical thinking and creativity. And it is also supported by surveys of many CEOs who really put the creativity as really very serious skill, which needs to be paid attention and systematically developed. Also within Industry 4.0, they are divided into several groups, from technical skills, data AI skills, and social competence, and nowadays interdisciplinary collaboration is strongly supported, as well as communication skills are necessary to develop, and leading towards personal skills, in spite of the fact that area of Industry 4.0 is rather technical point of view, but according to McKinsey and our service, we realized that soft skills are rather important to be in the center of attention, from problem-solving minds and to analytical thinking, and also capacity for abstract thoughts and so on. I would like to, the next one slide, please. Vega project, working competencies in the context of 4.0 development. Within this project, we try to identify new working requirements and also which skills and what kind of digital literacy will be required according to national qualification framework of the Slovak Republic within the context of development of technologies and within working industry environment, Industry 4.0. The aim of the project is to support flow of information between education subjects and markets, and by considering the need of innovative approach to the content of the education, which is based on intelligent industry strategy development. And aim is put on specifying these requirements according to national qualification framework and specific sector branches. Getting to the next one slide. As we told that within the Europe is really strong focus on collaboration and networking, we try to carry out our activities and project with European Alliance for Innovation, which we have established in 2013, close to Slovak University of Technology in Bratislava. And it is community which tries to support worldwide collaboration within putting the focus on common topics. In 2013, it was identified that the really area about Industry 4.0, smart city in Central and East Europe could be wide of the ways of collaboration. That's why YUA is on organizing summits of this for this topic, as well as to create project consortia. And I see this is really rather strong tool to find the common ways between our countries for strengthening our collaboration. And at this moment, I can also share very good news as far as Sami State University and our Slovak University of Technology, that just previous week we have received positive evaluation of our common project between Sami State University and Vera, also with Slovak University of Technology, that within Erasmus Plus, International Crowded Mobility, we have approval that it will be financed and that we will have a chance to deepen our collaboration between our universities. So I again see that it will be another space how to get closer within our common areas, within our research and helping with each other. And we realize that research needs community which also provides feedback, and it is necessary to push the ideas to the market and exchange with each other. As we agree that international scientific collaboration is rather crucial, also this is the way how we can continue, how we can find our following ideas, possibilities within Industry 4.0 and other areas. At this moment, I also want to express my sincere thanks to Associate Professor Vitaly Ivanov, as well as Ivan Pavlenko and their team, that we also started this journey on 7th International Conference on Mobility, IoT and Smart City in Krynica. And I believe this can continue with collaborating on this Industry 4.0 in conference organized by called Mobility, IoT, Smart City in collaboration with European Alliance of Innovation, very strong position also of Sami State University, where we can find common roots and continue via these topics I will ask for next slides, please, about conference mobility topics. Thank you. And leading towards sustainability. Next slide, please. And another project, next slide, concerning H2020 project, is linking research and innovation for gender equality in agreement with fifth sustainable goal. We realized that also this project, H2020, was also in accordance with Agenda 2030, where fifth sustainable goal is just gender equality. And our aim is to support research institutions, putting the focus on disciplines, science, technology, engineering, and mathematics in designing and implementing their gender equality plans, and also in implementing innovative strategies at the level of objectives and indicators at organizational level. Getting to the next slide, please. I have to say that the duration is for 4 years, and we try to develop strategy and implement awareness-raising activities and targeting to different stakeholders, such as research public organizations, research funding organizations, and policymakers and researchers within our consortium, where is lead partner from Greece, Vilab, and other partners like Smart Venice from Italy, or Young Academy of Europe, University from Brussels, University of Zagreb, or Institute for Research and Biomedicine in Spain, and many other partners. Our faculty is strongly involved within work package number 5, where we get from internal engagement and change management using the tool working groups. And we try to define and identify scientific role of middle management. In the following slide it is, please. And also engaging the innovation ecosystem, where we have a really strong collaboration with research and innovation hubs within Slovakia, but it can be also the starting point for deepening with some state university, and there is goal to implement win-win strategies and pragmatic synergies. And as far as raising awareness and engagement activities, there is also goal to create favorable environment for the acceptance of these gender equality plans measures, and we are getting to sustaining and replicating within STEM by using tool sustainability plans, and to getting to the charter of institutional change for gender equal research and innovation hub, which could be rather beneficial for the partners. This Caliper project, next slide please, has the role to ensure also the sustainability and expansion them, not only on local, but also at international level, where we need to target key stakeholders. A mission of this Calipers project is to design, develop, and implement sustainable gender measures. And also it is crucial to recognize the need for these measures that will lead to changes within organization and adopting innovative approaches and creating strong linkage between the academy, government, industry, and civil society organizations. At this moment, I would like to get our next H2020 project with title Directional Composites through Manufacturing Innovation, with acronym DSMIE, which we started to solve in March 2018 till February 2022. And aim is to bring together leading innovators from across Europe and beyond to be able to develop new methods of producing composite material parts with optimized fiber directionally. This project is 4 years lasting project. There is 17 partners from 11 countries, and with financing 1,426,500,000 euros. Next slide, please. As far as consortium, it is created from United Kingdom, like Library University or Cluj-Napoca, or Sweden, Lund University or Aachen University in Germany. From Ukraine, it is Kharkiv National Aerospace University, or together with Sabanikal University in Turkey and others. Next one, please. Also, the project H2020 is divided into several work packages, starting from specification of performances through composite material studies to designing hybrid manufacturing systems, leading towards prototyping and demonstration. At this moment, I would like to invite my colleague, Associate Professor Lacko Morovic, to continue and giving more detailed information about this H2020 project. Please, Lacko, the stage is yours. Thank you.
Thank you very much, Professor Tsaganyova. As we can see on the slide, the three main problem was to choose which advanced manufacturing techniques we will combine, which composite materials we would like to use, and how we'll work this hybrid manufacturing system. So it was, or still it is in the process to design this manufacturing system. The next slide, please. We decided to use the additive manufacturing technique. It's also called like the 3D printing, and the subtractive manufacturing. It's a part of the machining technologies, and actually we choose the milling. The question is that why it's important to combine these two techniques. The answer is that the additive manufacturing techniques a very good tool to manufacture geometrically very complex surfaces, but these technologies are not accurate from the view of the mechanical engineering. So by the additive manufacturing techniques, we can manufacturing a geometrically complex or complicated surfaces, but by the subtractive manufacturing with the milling, we can accurately manufacture not all the surfaces, but just the functional surfaces which are important for us. The next slide, please. Mainly today, nowadays, the 3D printers using just the XYZ coordinates to manufacturing the part, but the new idea in the frame of this project is to use expect the translational axis XYZ, also some rotational axis, and with the combination of these movements, we can also continuously manufacture the cured surfaces. The cured surfaces, as we can see on the picture or on the figure, with the green color, but the support material, because the support materials many times is necessary to use, will use by the flat layers. So just in the XY coordinations. The next slide, please. We will use the technology, the 3D printing method. It's called fused deposition modeling. So it's nothing new. It's it's a very common, well-known technology. When is extruded the material, in some minutes I will talk that exactly of which material we will use. And as you can see on the figure, the black part is now it's building on a skeleton. We have some questions, technical questions that we will need to solve to find a solution in this project, but I hope that it will be successful. The next slide, please. Now I would like to talk some ideas about the composite materials, because this project is mainly focused for using the composite materials. In this type, or in this case, we will use a matrix. This matrix material will the polyamide material, maybe the acrylonitrile, butadiene or maybe polyether ether ketone. We need to decide it, but I think that the polyamide will the winner in this case, and this polyamide matrix will reinforce it with the carbon fibers. And this combination of two materials will result a light material what we can use for in many fields. For example, also in the aerospace industry where you need light material but strong materials. The next slide, please. About the design of the hybrid manufacturing system, it's actually of our goal in our faculty. We are thinking that which kinematical structure to use in this case. It will a 5-axis hybrid manufacturing systems, but we need to also decide that it will four axes for moving the part and 1 axis to moving for the extruder or the milling head, or 3+2 architecture we will use. Also, a very interesting possibility is to use the robotic arm. So it's not used parallel systems or serial systems, but use a robotic arm. And what is very important to heat the building space, because some heat during the building process in the material can causes the deformation or cracking the building parts, what is not a good thing. The next slide, please. This is my last slide, and here I would like to summarize the key performance indicators. It's mean that new system, hybrid system, we're thinking to use for relatively small parts for maximum or minimum 200 times 200 times 200 millimeters. The polymer material reinforced with the carbon fibers will feed into the system in the form of filament with the diameter 1.75 millimeter. Fibers to be fed into a system in the form of commercially available bundles. So this system's existing, but we would like to change it for our goals. As I told, it will the combination of additive systems, additive manufacturing system, and subtractive manufacturing systems. First, it will be good to manufacture the parts with the minimal supporting material. It's also a question of the design, how to design these parts. The extruder head working temperature will approximately 460 degrees of Celsius. What is very important is the dust extraction during the milling operation of these parts, because the carbon fibers, to break the carbon fibers is very, very dangerous. The input geometry will the STL neutral format or OBJ neutral format, and this all hybrid manufacturing system is a low-cost system. This means that the maximum price will 10,000 euro for building these systems. Thank you very much, and I would like to give back the word for Professor Dagmar Caganyova.
Thank you very much to my colleague, Associate Professor Morovic, for his support and collaboration. And at this moment, I would like finally to express our sincere thanks once more to Sunny State University, International Association for Technological Development and Innovation, and personally to Chair of the conference, Vitaly Ivanov, for his great support, perfect organization, and really excellence and serious approach to any work he is carrying out. So sincerely, thank you very, very much. And also thank you to Professor Olaf Csiszak, Dean from Poland.
Thank you.
And thanks also to all other international partners with whom we have a chance to collaborate, whether they are Spanish or all other partners with whom we thanks also to Ukraine, Sunny State University had a chance to collaborate. And I believe that it can be also impulse for finding new inspiration for collaboration in future common projects or any way of collaboration of deepening and strengthening innovation and networking with each other. So thank you very much once more, and wishing great success to this third conference. Thank you.
Thank you, dear Dagmara, dear Radisław. The greetings from the Poland, from the Ukraine, of course, from the whole of the world.
Thank you very much.
Everything is good. From my side is a congratulations for the very nice and good project, scientific and financed. This is very important to resolve very social and manufacturing problems with the Industry 4. And now is the time for the questions. I look on the chat, on the Skype chat. I don't see anything. On the YouTube chat, I don't see. I think everything was clear to us.
Thank you. Thank you very much.
Probably. Thank you once more for your presentation. Thank you.
Thank you. Bye bye. And wish you
Bye.
success.
See you on the normal.
Thank you.
Thank you. Thank you. Bye.
Bye bye.
Bye bye. Radisław. My dears, it's time to the third keynote speaker. It will be Professor Mateusz Barczewski from Poznań University of Technology, my colleague from our faculty. At the start, of course, a few words about Mateusz. Mateusz is a researcher at the of the Institute of Materials Technology, Faculty of Mechanical Engineering of our university, Poznań University. His research interests at the development of novel polymeric composites and biocomposites, waste management, and rheological measurements. More of his work was focused on the realization of several projects financed from regional and European Union funds, as well as international European project from the 7th Framework Program. As a project manager, he coordinates works in the project realized under funding of National Center of Research and Development of Poland over the development of novel biocomposites for the automotive industry. He is a journal editor of the special issues of GCR indexed journals and author of more than 70 scientific papers published as monographs, conference proceedings, and papers, including more than 50 peer-reviewed publications in GCR indexed journals. Dear Mateusz, Professor, the stage is yours, internet is yours, please. You can start. Oh, sorry. The title of your speech is Application of Basalt Powder as a Perspective Low-Cost Waste Filter for Polymeric Composite with Lowered Environment Impact. I think I read it correctly. Please, you can continue and correct if it is possible. Proszę.
Good morning, ladies and gentlemen. Thank you for this kind introduction. This is a really great pleasure for me and a great honor to be the keynote speaker of this conference. I hope that my presentation will be interesting for you, especially that the topic is much different than previously discussed by my speakers. I came from the Poznań University of Technology, and we are actually one of the biggest technical universities in Poland. We offers education in 9 faculties and running over the 30 fields of the study. We actually learning more than 16,000 students, and over 1,300 academic researchers are working on this university. I think that we are in many fields we are quite strong in this moment, but I will focus on my field, on the field of the material science. And may I ask for the changing the slide? Okay, so as I said, today I will talk about the different approach that those presented by my previous speakers. I will tell about one of the topics that is dealing with our group for almost 8 years, from the different topics, including manufacturing of the nanocomposites, polymer processing. Since few years, we focus on the development of the sustainable materials and finding of the new ways of utilization and valorization of the waste generated by various branches of industry. And in fact, it should be underlined that we're working on looking for the new materials for the sustainable development of the composites. So we used mostly waste from the agricultural industry, but also from the mining industry. And the choice of the topic was not for today's speech. It was not random, and I will now ask for changing the slide. I think that most of the people who are working with the composites, when they hear basalt, they think about the basalt fibers, and when we think about the basalt fibers, we think about the Ukraine, which is the biggest producer of the basalt fibers in the world, and the country where the basalt fibers were developed in 1960s. And what is the basalt? Basalt is a volcanic solid rock with the affinite structure, with the highly compressive strength and the high hardness. Mostly in Poland, we do not produce the fibers, the basalt fibers, but it is used for the production of the broken aggregates for the asphalt mixers or the crushed stone for railway. Unfortunately, the huge amounts of the basalt powders as a waste without way of the utilization are generated. And a few years ago, we started, after working with the basalt fibers, the Ukrainian basalt fibers, of course, we start to thinking, is it possible to achieve even some of the benefits from using the basalt fibers by replacing them by the low-cost filler in form of the basalt particles? And maybe now we'll change this slide again. So we will start thinking about the basalt powders taken from our local supplier from the mining in Wilkowo in Złotoryja. We achieve with the chemical composition as it presented in the slide. Usually the chemical composition of the basalt is quite similar, despite it is deposited in the various places in the world, in Ukraine, in Russia, in Poland, in China or United States. The chemical composition is quite similar. It's mostly built from the silica and aluminum oxide. We actually use the material that can be often taken from the different mines as a material with zero cost, because it is a waste. Actually, we work with the material which costs about 20 euro cents per kilogram, so it allows us to reduce significantly reduce the price of the final product. And this is our goal, to produce the materials with the low cost, with the beneficial properties in comparison to pure polymeric materials. And maybe now I will ask again for just changing the slide, and now we can see that we work on the material that was preliminary sieved. So we have we can see here the particle size distribution of the materials. So we work on the small particles. We can say we work with the dust, so the materials that can be used as a fertilizer for the landfill, or eventually it can be used for the creation of the concrete structures. However, it's still not commonly used for industry, and there is a huge potential in this material that we decide to work on it. Okay, and now we will change again the slide, and here we can see the path of the modification of the material. If you think about the production of the composite materials that are based on the waste fillers or the waste materials, we must change our thinking. In fact, we cannot use the really cheap material and modify it to achieve the really good properties of the composite, but we must look for the proper composite for this filler to exclude the additional operation that may increase the cost of the materials and make it more or less competitive with the commercial and synthetic materials. So here we can see that the typical path is based on the mechanical processing and the chemical modification of the filler. Of course, each time we must make the really in-depth characterization of this filler. And now we can change the slide. And what will occur? Usually, we must reduce the chemical modification. Unfortunately, if we change the slide, we will see that chemical modification. Oh yes, it will be out of here. And in fact, the chemical modification in our studies was reduced. We, of course, make the surface modification of the filler, but the results were not reasonable from the cost point of view. The environmental impact was reduced. The water and the carbon footprint on the final products was also worse than the materials without this chemical modification. The mechanical properties, the thermal properties were almost the same. So in later studies, we only make the preliminary sieving and grinding of this material. And basalt powders in the form of the fine powder was incorporated to various polymers, and we can see that we use the thermoplastics, including biodegradable polymers and non-biodegradable polymers from the petrochemical industry, as well as thermosets. So, as I said, we use the wide range of the polymers in order to find the best application and to find the application that will be interesting for our industrial partners. Okay, now we can change the slides, and we will see about the information about the various polymers that were used. And if we see on this see this slide, we can see that we incorporate usually as much filler as it's possible. We usually bring more than 20% of the filler, so usually from 5 to 40%, even 70% in some cases, and we incorporate this filler into various polymers. So as I said, thermoplastic polymers such as polypropylene, so the typical non-polar material with the high ability to create the crystalline domains, the PLA, so the most commonly used and most perspective biodegradable polymer in the industry. Then we move to the thermosets, so the materials that should be replaced as much as fast as possible. So using the development of the different highly filled composites gives an opportunity to reduce the amount of these non-biodegradable materials. We use the epoxy resin, which is mainly known from the production of the lightweight constructions and composites reinforced with the fibers. So we use the basalt powders as the as a source of the hybridization of this kind of materials, as well as can be used for the electronics. We work also with the polyurethane for the spray foaming applications, including the creation of the thermal isolation of the buildings, and polyurea spray coating materials, which will be discussed also later. So now we can move to next 3 slides that will show us how we prepare all the mixing procedures. Is really important from the point of material science and final products. In case of all studies, we simplify the procedure as much as is what possible, and of course we work on the laboratory equipment, but we did not use any typical laboratory operations that cannot be used in the industry in the larger scale. So in case of all of the thermoplastic materials, we make the preliminary mixing of the filler that can be realized by the gravimetric feeding system in the commercial machines. Of course, all materials were dried before the mixing in the molten state, and then we prepare the compositions by twin screw extruder and form the samples by using the hydraulic injection molding machine with the parameters as presented in the slide. So now we can move to another slide, and we'll see that the creation of the epoxy composites is also almost the same like in the industrial conditions we use, or not. We didn't use any sonification method or different really mixers that are typical for laboratory scale. We use the big mechanical mixer with the high rotational speed. All compositions were degassed, and then we prepare the composites by means of the casting procedure, as well as the hand layup or resin infusion procedure. As you can see in the lower part of the slide, we can see here the laminates that are reinforced with the aramid fibers and the basalt fibers that are based on the compositions containing basalt powder and epoxy resins. Of course, all of those materials should be post-cured. And at the last, I think I should talk also about, when we change the slide, I can also talk about and say about, I think, the most important from presently realized studies and work applications. So using the basalt powder as a filler for the polyurethane and polyura spray coating composites. Actually, we are after the realization of the quite big project with our industrial local partner, and we prepare the composites containing basalt powder as a filler for the materials that will be used for the creation of the reinforcement for the spray coated reinforcement of the pipes for the water supply. And usually we use the basalt powder, we incorporate basalt powders into the polyol or polyamine. We prepare the mechanical mixing, and after that, depending on the preparation method, we use the mixing with using the static mixer and spray coating, as it can be seen below. Now, in this case, we can see that we are using the spray coating by small laboratory spray gun. However, also we are after the realization of the industrial process, and in this moment, this material is applied in the industrial conditions, and it is commercialized. Okay, so what is quite interesting here, and in case of the old thermosets, basalt powder seems to be reactive, but I will talk about it later. And now, if we change the slide, we can see when we discuss the common changes of the modification ways that were observed for all of the materials, because it's quite easy to find the material, the pair of the polymer and the filler that will be actually passing to each other, and we get the beneficial results. However, some of the changes of the properties were comparable and comparable for all of the materials. So the first approach that was the most important for us was the improvement of thermomechanical stability. So extending the field of the application of the material by increasing the temperature of its use. So we improve the stiffness and elevated temperature. We check it and we measure it in the static and dynamic condition. We can see that 3 different methods are meant here. So Vickers soft-netting temperature determination, heat deflection temperature, or dynamic thermomechanical analysis. Here we can see also the collectively presented the results for 3 different polymers with various techniques. So we can see at the top of the slide the variation of the Vickers soft-netting temperature and HDT of the isotactic polypropylene-based materials. And here we can see more than 20 degrees improvement of the Vickers soft-netting temperature, which really improve the usability range of this material. The same phenomena can be observed for the epoxy composites showed on the left bottom slide of the left bottom part of the slide. So we can see here the DMA curves of the epoxy resin composites. In case of in case of the highly porous structures of the polyurethane, the changes of the storage modulus, so the stiffness modulus, were improved by incorporation of the fillers. So for all materials, this is the property that will always change, and this is the same phenomena as can be achieved by using the basalt fibers. And when we move to the next slide, we can see another property which is extremely important from the application point of view. The biggest weakness of the polymers is their low thermal stability and high flammability in comparison to metals or ceramics. So we prepare the wide studies of the flammability of how materials behave in the fire conditions. And here we can see the polypropylene composite samples with the 20% of the basalt powder during the course of the cone calorimetry test, which is the most commonly used method for determination of the fire behavior of the materials. And in all cases, incorporation of the highly temperature stable filler in form of the particles reduce the amount of the fuel for the burning and reduce the heat release rate. Unfortunately, in many cases, as can be seen from the graph, we can see the time to ignition was improved due to the higher thermal conductivity of the material. However, if we look in the next slide, where the result of the epoxy composites are presented, the results became much more promising. And if in fact epoxy composites are those which are mostly used in the automotive automotive industry, in the airplanes, so where in the place where the flammability is essential from the safety features. And here we can see that addition of even 10% of the basalt powder significantly reduced the flammability. The samples were discussed, and they were self-extinguishing during the exposure to the fire. At the bottom of the table also we can see that the mean total heat release evaluated by microcalorimetry was also reduced. So maybe the addition of the basalt powder did not create totally inflammable materials, but in case of the hybridization and using the different intumescent flame retardants commercially used, we can obtain the low cost and safe materials for the different branches of the industry. And if we move to next slide, so we can see that the thermal degradation was also decreased. So if we talk about the flammability, we always think also about the thermal stability of this material. Of course, even if we achieve the higher thermomechanical stability, so the stiffness of the material is increased in some conditions, in elevated temperature, it is really important to achieve also the higher thermal stability. And for all composites excluding polypropylene, the effect was achieved. The higher content of the basalt powder, the higher thermal stability. And here we can see the result for the epoxy resin, and here we can see more than 20 degrees improvement of the thermal stability of these materials, assessed as 25 mass loss of the composite during the thermogravimetric test. And if we move to another slide, we can see also that not only the mass loss was temperature characteristic for the mass loss was increased, but also the thermal degradation kinetics evaluated by the different models, including Ozawa and Kissinger models that were presented here. Well, the activation energy of the degradation was also improved. So this is really good information for us. Even if we check at the next slide, the results of the thermal degradation realized by the thermogravimetry for polyurethane foam, so the material that is broadly used in the civil engineering for the thermal isolations, we can see that the thermal stability is significantly improved. So also we can use this material as a safe thermal isolation material. When we move to the next slide, unfortunately, we can see also that not for all materials these benefits can be achieved. For some materials, such as isotactic polypropylene, we can see that the agglomeration of the filler occurred, and in fact the particles became in the mutual contact, and the thermal conductivity of material was increased, and therefore also for more than 20% of the filler, the thermal stability was decreased in comparison to pure material. However, it's also good information, because even if we incorporate 5% of the basalt powder, we can see that the thermal stability is increased, so we can find a specific application for this material. So I think all of you thinking, because we are on the conference including the mechanical engineering, so the most important property, how the stiffness of the material, how mechanical properties change. And if we move to another slide, we can see that as it can be expected, the hardness of the material, in this case I present the example of the isotactic polypropylene, was increased, as well as the Young modulus, so the stiffness material is significantly increased. And those two phenomena were observed for all of those materials, for polyurethane, for the epoxy resin PLA. In each case, the hardness and then stiffness of material were improved. And what should be also underlined, of course, incorporation, addition of the particle-shaped filler usually causing the decrease of the mechanical properties of the materials. In this case, the deterioration of the mechanical properties was observed. However, the reduction of the final tensile strength was not strong enough to exclude those materials as a composites for the development and production of the various constructions materials. And when we move to another slide, so I think the most perspective way of utilization of these materials in this moment that we are working with our industrial partners, as well as the Krakow University of Technology, is development of the spray formed rigid forms for the thermal isolation, as well as the polyurethane material for the reinforcement, achieve the high impact strength materials for the pipelines removal. And here we can see that on both slides that even additional 30% of the filler and the top graphs, we can see that even if we incorporate 40% of the filler, the thermal conductivity is not changed, and it's changed, but not enough to exclude this material as a thermal isolating material, due to the partial reactivity of the basalt fibers and changing of the pH of the polyol composition. We can reduce more than 40 or even 70% of the petrochemical materials and make the polyurethane spray forms much more sustainable and environmental friendly. So this is really big achievement, even if we see that the compressive strength of the material is a little bit lowered. Those properties are still at acceptable level, and we must remember that we are at each time we replace the 10 or 40% of the polymer that are in the composites by waste material, we achieve the materials that are much more that are characterized with much less environmental impact and lower carbon footprint. Okay, so then if we move to next slide, we can see also that addition of the basalt powder compensate the lack of the part of the polyol, the hydrogen bonds that are contained on the chemical structure of the material, shows us the comparable structure of the final products. So this is really important. The content of cells, of closed cells that are responsible for the thermal conductivity, is almost not changed, and the structure of the material is also almost the same as in case of the unfilled polyurethane. So this is also really good information for us and our industrial partners. And when we move to the next slide, we can also talk about the compatibility of those systems, because in most cases, addition of the fillers that are not chemically modified, and when we incorporate it into the various, especially thermoplastic hydrophobic materials such as isotactic polypropylene, results in the weak adhesion between the filler and the in the matrix. Here we can see in the bottom of the slide that the particle is well saturated by the polymeric matrix. This is the cross section and the scanning cross section of the sample and the scanning electron microscope image taken from the composite. And we can see that the particle is well saturated by the filler, even in case of the second second case of the PLA, so using the biodegradable material, when we compare the basalt fillet composite with 10 to 20% of the fillet with the composite containing 20% of the basalt microfibers, we can see that in both cases the samples are well saturated in the first two photographs after annealing. So the thermal treatment of the amorphous materials that is realized in order to achieve the crystalline structures, we can see that adhesion in case of the basalt particles is not totally loose. There are not pull-outs of the fillers. In case of the basalt fibers, the adhesion was totally loose. The properties were much more worse in case than in comparison to the basalt fibers materials. And when we change the slide to the next one, of course, we can see that in case of the reactive system and thermoset materials, the samples due to the partial reactivity with the monomer in case of the isocyanate-based materials, so the polyurea and the polyurethane are well saturated. Here we can see the epoxy composites where the cross-link density around the particles is much more higher. So we can see the amine hardener reacting with the hydrogen bonds and give us opportunity to achieve really good adhesion around the materials. So the reinforcement and the improved hardness of the filler is not only the effect of the presence of the rigid structures, but also we change the chemical structure and chemical cross-linking of the final product. Okay, so to conclude, if we move to the next slide, we can see that even if we use different materials, it can be polypropylene, it can be hybrid composite containing glass fibers and the basalt powder incorporated in the polypropylene, PLA, epoxy resin, rigid polyurethane forms or elastomers manufactured by the rotational mold, reactive rotational molding, or spray formed elastomeric coatings. Similar effects can be achieved. So the thermal stability, thermomechanical stability will be always achieved. The thermal and the flammability will be reduced. And one phenomena which I am not talking about in this moment, but is extremely interesting, and we are still trying to understand all mechanisms that are occurring in this case. The processing properties and rheological properties of those materials are not so strongly influenced as it should be supposed. Usually when we incorporate on edge the 20 or 30% of the silica on various fillers into the material, in the polymer materials, the processing of those materials are really weak. So the processing properties are strongly suppressed. In this case, this phenomena did not occur. So we can achieve a composite with the more than 40% replacement of the polymer, but the properties and the processing properties that are comparable to unfilled materials. So this is really important from the application point of view. And when we move to next slide, where all of those conclusions are also contained, we can see at the bottom of the slide that there is only one, maybe not only one, but the biggest weakness of these materials. Unfortunately, the basalt particles are quite hard, so they're really hard because it's more than 8 in the Mohs scale. So there is a risk of abrasive wear of the processing tools. But if we recalculate whole process and the benefits that can be taken from the changing the properties of final products, the reducing its price, even if we must include the modification of the fixing of the tools and the machines, the process still is reasonable and can be and is applied by us and our industrial partners in this moment. And then if we move to the next 2 slides, I want to thank for all of my colleagues because it is impossible to make such a huge amount of the work without the cooperation, and most of the work was realized by the funding of the ministry, funding of our that is placed in our department, that is given by our dean Olaf Ciszak after the realization of the project of the Ministry of Science and Higher Education. In this case, we cooperate also with the Polytechnic of Krakow and the Central Institute of Labor Protection in the Warsaw and the Technical University of Bydgoszcz. And when we move to another slide, we can here see the different project also, that because in case of PLA, as it was kindly said in my introduction part presented in the Ciszak, the PLA part and modification of the composites based on the biodegradable materials are undertaken under the project of development of hybrid biodegradable composites manufacturing technology industry, as well as the polyurethanes and polyurea are also financed by the European Union under the project Quick Setting Hybrid Composites for the restoration of pipelines, including ground-based and vacuum ones, which was realized in the last year. In this moment, we are during the commercialization of this project. So I hope that I make this waste work kind interesting for you, and feel the taste of waste, and appreciate this as we in the last few years, when you understand it was not using working with the waste is not a waste of the time, but it's our future. So again, I want to thank for the possibility of presentation of our results. It's an honor to be here with you online, and thank you for your attention. We can move to the last slide, and thank you very much.
Thank you, Professor Mateusz Barczewski. Thank you for your very interesting and, of course, important speech for your researchers in our university and, of course, with your team, scientific. Maybe some questions to Professor Mateusz Barczewski. I look on the chat, Skype or to YouTube. I don't see any.
No questions.
No questions.
There is one question.
Almost clear for us, but Mateusz is very young and ambitious scientist. I trust him that the environment in the future and of course the materials will be better.
Maybe I will answer one question, because it is right here, because there is a question about the deposits of the basalt. Of course, in Ukraine, there is a huge amount of the basalt, much higher than in Poland. Actually, we work with the basalt taken from the Złotoryja in Lower Silesia in Poland. So.
Okay, thank you.
Thank you.
Next question, maybe?
No questions.
No questions. That's, my dear participants, dear keynote speakers, at this time is to finish our first session. I was very happy and proud to provide this keynote session. Thank you, Vitaly, for the invitation to be a chair of this session. Thank you once more for all of the participants of the DSMA third conference, international conference in the Ukraine. Thank you once more.
Bye.
Dear Olaf, thank you very much for serving as a session chair. Everything is perfect, as always.
Everything was perfect, prepared by your side by your team, and of course.
Dear Olaf, please don't end call. We would like to proceed to the next session award ceremony. I would like to introduce our rector, Professor Anatoly Vasilyev, and he would like to make some information.
Шановні колеги, я хочу скористатися цією нагодою і виконати приємну місію. З професором Олехом Чішаком у нашого університету давні партнерські стосунки. До речі, він був і спікером першої конференції. У нас потужні наукові стосунки і по проведенню самих різноманітних заходів по сумісним науковим наробкам і таке інше. Враховуючи все, наш університет, вчена рада нещодавно прийняла рішення про присвоєння почесного звання почесний доктор Сумського державного університету, шановному професору Олафу. Я з великим задоволенням в цій віртуальній реальності вручаю шановному нашому колегі оцю ознаку, диплом університету стосовно того, що професор Олаф Пішак є почесним доктором Сумського державного університету. Вдячний за співробітництво і впевнений, що воно буде тривати далі і розвиватися.
Okay. Yes. Thank you. I turn on. Nie cudujcie. Thank you. That's the time for me, I understand. Can I say a few words to our community, to the participants of DSMIE and the Sami State University community? Can I start? Okay, thank you. Rector Magnificence, High Senate, Dean Gusak, Sami State University academic community, and our team, Vitaly, Ivan, and Alexandr, DSMIE participants. With great surprise and joy, I accept the degree Doctor Honoris Causa of Sami State University. For me and the international team, the highest distinction inspires us to continue working together. I decide this success to everyone involved. Interactions with people have shaped me as a person. My knowledge, life experience, sense of humor, distance to myself, all of my success have been influenced by the people around me. As Adolf Herneck said, nothing strengthens a man more than the trust shown to him. Thank you for your trust. In today's world, and especially under pandemic, it is difficult to cooperate, but we have shown it is possible and can bring remarkable results. This conference is an example of what can be achieved through cooperation, even during challenging times. Let us support the conference motto, together we can more, and develop modern solutions that respond to the needs of the environment. My friends, let's keep working together for the common good. Ladies and gentlemen, thank you for granting me the honorary degree of Doctor Honoris Causa of Sami State University. This is a great gift for the academic community. Thank you very much once more. To see you maybe in the future in the normal environment. Thank you.
Dear Olaf, thank you very much for your thank you speech. We appreciate your support and your significant contribution to development of international collaboration between our universities. Your initiative is very appreciated and we are very grateful for this. Thank you very much.
Thank you very much. Of course, we can do a little more with success because we're working together in the one team Poland and Ukrainian. And I say the last conference, I love Ukrainian, if you remember. Yes, yeah. It's a good contribution with our universities. I have a present with my friends and they prepare a little gift for me, some flowers. I understand it's from the Ukrainian side, okay? Yes. If you see?
Yeah, we see. Thank you very much.
Thank you very much. Thank you. Thank you. Dzięki.
Thank you.
Chodźcie, to jak już robią zdjęcia tego fotograf, no dalej. No. Dobra. Gdzie na tym? Tu? Tak. Chcecie jak swoją.
Скажи пусть.
Ladies and gentlemen, I would like to, now I join to this conference and I am chair for this section. And first speaker is Aaron Najara Reach from University of Duisburg. And now is time slot for you, Arun. You can start, please.
Okay, thank you, Milan. And yeah, welcome also from my side to the DSMI for this year. And it's really a pleasure for me to be part of the DSMI conference this year, even if this is online. I already said it was a great pleasure for me to be part, the personal part of the last year DSMI, and hope that we will meet us together in the next year. So, and also, Vitaly, thank you for the invitation. And now I have to switch to my presentation to have a look on my presentation. Who is guiding me with my presentation? Can I have it? Okay.
Okay.
Okay. Okay. So. Okay, understood. So then I will start, and my topic for this, or for my keynote, is a digital twin, a scientific view. But before I start with my presentation and with the core topic, I would take the chance to introduce the university, my university, and also my institute, because I think the city Duisburg is not that well known in this round. So I will introduce the University of Duisburg-Essen, then I will introduce my institute, and then I will go to the core topic of my today's presentation. This slide with the topic, the heart of Europe, should show you that we are really sitting in mostly in the middle of the Europe. And if you look at the distance to Belgium, like Brussels or Amsterdam and so on, it's really near to Duisburg. And so we say we are in the heart of the Europe. And if we talk about the area or the city Duisburg-Essen, then we have to talk about the area Ruhr. And the area Ruhr was in the past very famous for coal and heavy industry. But you know the situation, probably you should know the situation in Germany, that we are changing from our coal industry to new industries, and one of the specialization is the service industry. So it was the idea is to change this region coming from the whole coal and heavy industry to service industry. And to support these changes, in the 15th and the 16th of the last century, there were universities founded, and one was in Duisburg, one was in Essen. And that is also the idea to support the change of this area. And in Duisburg, it's around about 500 inhabitants, and still the most important production site in Europe. And also we have here, we say the inland port in Duisburg is one of the biggest inland port in Western Europe. And also we say the Silk Road ends here in Duisburg. So therefore we have this kind of big inland port in Duisburg. And so the logistic is one of the core topic also in the area of Ruhr and also especially in Duisburg. Essen, and if you can imagine how area with coal should look like. And it was really impressive from our side that we can now say that, for example, Essen was elected as the green capital in Europe in 2017. And this also shows the change that we are doing today from a coal region to really a new changed region. So the next slide, please. And now some facts and figures to the university, and some to the facts and figures to the university. It was established in 1972. As I mentioned before, this was the idea to change the region, so the region needs universities to develop new kind of thinking, to develop or to implement new technologies in this region. And beginning from January 2003, we merged, means the Duisburg University merged with the University in Essen and to the University of Duisburg-Essen. And we are really proud that we were elected in 2019 to, in the time higher education, we had the 14th place as one of the 14 best universities that are young universities. And we plan also to extend our collaboration to other universities in the near, a well-known city. If you're interested in football, then you know the city Dortmund. And Dortmund is around about 50 kilometers far away from Duisburg. So the idea is to extend the collaboration within the universities in Bochum and Dortmund. And I will come later to the facts and figures to this topic. Next slide, please. And now we have some facts and figures only for the University Duisburg-Essen. We are around about 40,000 students with around about 500 professors, with around about 307,000 academic staffs and so on. Our yearly budget without the medicine faculty is around about 360 million euro. That is just only for University Duisburg-Essen. Please go to the next slide. And here you see the students by department, and the engineering department is one of the biggest department within the University Duisburg-Essen, and we are roughly around about 12,000 students within the engineering faculty. Next slide, please. So here you see the cooperation, the University Alliance Ruhr, as I mentioned before, and the idea is to become one university within one roof, or 3 universities within one roof, and the roof is the University Alliance Ruhr. And the facts and figures to this alliance will be that we will then have around about 500 courses. We will have around about 120,000 students, and we will have 16,000 graduates with 1,300 doctorates, and our whole budget will be around about 1.4 billion euro. And we have here joint researchers already in the field, for example, materials chain and so on. So as you can see, our idea is to become one university roof within our area Ruhr, because the cities like Bochum and Dortmund, it's around about 30 kilometers to 50 kilometers to Dortmund. So it makes sense to have one university in this region. Next slide, please. Here you see our current active partners. So we support, and in the University Duisburg-Essen, we support the collaboration with universities from abroad. So we have 99 active partnerships worldwide and all over the world. So it is very important to really be part of the international community. That was just, next slide, please. That was just to show you our university, so that you have a little bit more idea and more picture about the city and the region we are based on, and also about our university. So please go to the next slide. And on this slide, you see our department, and our department IPE, so Integrated Product Engineering. And our institute consists of 5 shares, and we try to cover the whole topic coming from the conceptual design to logistics over additive manufacturing or plastic manufacturing. And we are around about 65 employees within our institute. Therefore, there are 50 PhD students. And in total, we have around about more than 100 PhD theses within the last 15 years. And we have a yearly budget around about 2 million euro per year. So that are facts and figures to our institute. Next slide, please. And that is to show you our research topics. And here you see the word smart engineering. Smart engineering is one of our core research topic. And what we understand behind smart engineering, that we see that to solve a problem in the development phase, we have to focus on 3 pillars. That is 1, process, methods, and tool. And if you look on processes, then you see that we try to model and simulate engineering processes. So our focus is clear on engineering processes. And we try also to consider today your development is not on one place, is round over the world, and also how to collaborate in such a network, which is worldwide, or that is worldwide, and how to optimize this process. And if you want to optimize this process, then you have to think about the methods, how you can support the process. And within the method, we focus on 3 topics. One is model-based definition, means how to bring all information within your modeling part. So it means that you will not have in the future technical drawing, how to bring this information into a model. The second topic is digital twin or product lifecycle management. I will come later, that I have the same understanding between both words. And the third topic is the model-based systems engineering. So how to model all activities within the model. And one topic within the model-based systems engineering is smart standards. That means how can we change the way that we are working today with the standards. Today, you have only paper-based or PDF version or XML version of the standards, and how to bring in a way that the machine can automatically get this information out of these documents, in future out of these models. And if you have these methods, you have to think about how to implement this in the tools. And in the tools, we focus for sure on product data management tools, the CAD tools, and also tools like data mining, or today you'd say data analytics, methods to identify your information that is needed to optimize your process. You see that all the things, the 3 pillars, process, methods, and tools, are connected together if you want to solve a problem within the engineering area. So, would you please go to the next slide? Now I will come to the core topic, the digital twin. And here I will show you first from the industry perspective, what is my understanding behind digital twin, before I show you what should be the focus from the scientific view on this topic. The next slide, please. Here on the slide, I have shown you the different scientific definitions that you will find if you look for the definition of digital twin. And here you see a list of definition from Elisa Negri from Italy and her research group. They analyzed the different definitions. And it is not important that you see the information on the slide. It's just to show you there's not one definition to the technology digital twin. There are a lot of definitions. And she worked out that the definition addresses different topics or focus on different topics on the digital twin aspect. One is to support the healthy analysis for an improvement maintenance. So the focus is on the maintenance side. And one topic is the digital mirroring of life of the physical entity. So the idea is to have the digital mirror of a physical product during the whole life cycle of the product. And the third thing is to support decision making through engineering and statistical analysis. So just for your making your right decision and to have this kind of digital twin. So that are the three focuses she worked out that these considered the different definition. And what is the core understanding? What is the core understanding of the digital twin technology from an industry perspective? And I will start with this, with an example. Would you please go to the next slide? And in this slide, you should see, you see the example of a navigation system or Google Maps. And I will try to focus on what is, or what are the core aspects in the context of digital twin out of this example. On the left side of on the slide, you see a paper street map. And in the paper street map is a static visualization. And static visualization of all information that is needed to come from destination A to destination B. And the important information, how to get as soon as possible from destination to destination B, has to be calculated by the user. So you have all the information, but to get the right information is done by the user. Even there were also street information for big cities, but there were not that information for smaller cities. And to be honest, the Y and Z generation does not know how we survived in this time. And in this time, we usually ask pedestrian to get the right house, the right street in a smaller towns and to get your address. And we get the situation on the roads, like how is the traffic on the highway or big cities. We get this information out of the radio. So we have to start our radio, we have to hear to the information, and there are traffic information, and now we see, oh, there's a traffic within my road, so I have to switch to another road, and so on. All this decision and all this calculation is done manually. The next evolution of this was the navigation system, the GPS-based navigation system. And now we have optimized different things. First, we were able to have dynamic maps. So in the past, if you want to go to all streets, so they have a lot of maps you have to use to have all this map from the cities, from the different countries, and so on. And this problem we have now solved because we have a hardware, and this information can show now in a dynamic way. And even smaller streets, small towns, and all this information were in the navigation system. So this problem was solved a little bit. So we have now solved one problem, but we were not able to, the calculation was also supported, the calculation how to come from destination A to destination B, the speediest way, the shortest way is also calculated. So one thing that we have done manually in the past was also supported by a device. And with the evolution of the navigation system, we get the TMC technology, so the traffic message channel. So the information that were given in the radio, this information was transferred with the FM to your navigation system. So you were able, so this system was able to calculate this information and to calculate your road according to the traffic information. And how you get the information to the traffic situation, there were a lot of technologies. One technology was, for example, that they have they had integrated induction loops in the roads, that there were sensors in the bridges to know these things, and so on. So this was a system that you should support to solve a problem, to know a better view on the real situation for the traffics. The third evolution that I would think the most of us use is Google Maps now, or from the automotive perspective, the RTTI, real-time traffic information. And now we solve the problem, or we had the situation that the traffic information in the TMC was quite okay, but with the evolving of the technology, we can optimize the situation. And according to the situation, we use now, for example, the smartphone of the users to get a better view on the roads, or the realistic view on the road, so we know how the real situation on the roads are, and now we can calculate much better the traffic situation and to find a solution for us. And if we look at this situation, or at this topic and at this example, what we learn out of this example, first thing is, to fulfill the purpose of a system, we have to extend our view of the system. So not the map solve the problem at the beginning, the map with you as a human being solve the problem. And now we see the human being was a manual activity, and we try to automate this manual activity with the evolving of technology. The first evolving with the TMC, we are able to have sensors or induction loops in the roads to get this information, to take the manual activity and to automate this. And also the calculation, which was done by our own, was also done now by the system. And this is one thing we should, or that's one thing we should think about if you go into the structure of the digital twin, to see, okay, we have a hardware, we have a product, and we have a service. And the service is done today manually, and the question is how to automate this manually approach. And this idea we try to implement in our industry areas. And therefore we defined a 7-step approach. Please go to the next slide. And in the 7-step approach, we say what we have to do at the first we have to define our system. What is our system? Is the system our product? Is the system our solution in combination between the product and the service? And that is our understanding. And now define the purpose of the system. Why we have this system? We have a navigation system because we want to get in a best way from destination A to destination B. And the third thing is identify the current proportion of the product and service to fulfill the purpose. So, and now you have to check which aspects are done with the service and which done is with the product. So as to see this as a, it's not a new word, as a product service system. And the fourth step is focus on the service part and determine the current maturity level of automation. So to see if we have done this in an automated way or not, and to check if not, is there enough potential to do this as a digital twin. And the fifth step, that will be, you will not do this in the scientific area, but from the industrial perspective, now the question is, do we have a positive business case? Make it sense? Is it good for the company to do this activity? So to make a business case, and then you know out of the business case, what could be the target cost for your technology development. And now in the sixth step, you go to developing your system, to design your system. And if you have done this, that we learn out of my example with the navigation system, and the navigation system, we can regularly ask if our technology is evolving, can we use a new technology to optimize our service process in a better way. So if we see that we have now our smartphones, we can use it to optimize the situation that we had in the past. So this will be a regular question that you ask regularly to optimize the situation. So this is the 7-step approach to implement for a digital twin. Please switch to the next slide. And this we have done in one research project. In this research project, we have a cell cooling tower, and in the cell cooling tower, we go the 7-step approach. So first ask, what is the system? In this case, the maintenance of the cooling tower. So we focus only for one company and what was really the product of this company, not on the whole system solution. Therefore, it is important to define your system boundaries, what you are really focused on. Then the purpose, for sure, ensure high quality maintenance at competitive cost and with low downtime. And the third thing is, in this question, the proportion is only service, because this company is doing this as a service. And what then analyze what they are doing today. Today, it's mostly paperwork work. So they are going through this cooling tower and document all the things that you see there. They make photos, they make videos, and so on, and then go back to the office, document all these things, and so on. But there's no connection, or there's no information flow in a whole way. And now we work out a business case and to see what is really the benefit out of these activities. And we see a lot of benefits. We can save a lot of time, and we can ensure or make the quality better, or we can reduce errors within this process. And that we have done with the solution. It worked on a HoloLens base, means now the experts go with the HoloLens according to this cooling tower, document all these things, all this information that is necessary, for example, for maintenance. And then this information is connected with the model, and this model has all information in structured way to combine this and to document all this information in a product data management system. So we have now in the product data management system, with every maintenance activity, we have the current situation and the real situation out of the real situation for the cooling tower. And therefore we document, as I mentioned, our digital twin in the PDM system. So the next slide, please. And here you see the hype cycle from Gartner. And in the hype cycle, you see the digital twin. And the digital twin is on the top of the evolution process. And this hype cycle show you, is there a hype in the technology, or really you can use this technology? So if you are in the later phases, then the realistic view on the technology is there, and you can go through for implementing this really for an industry application. So, and now we asked ourselves, is the digital twin from the scientific view something new, or do we have it already? And we see there's a lot of similarity with the PLM approach. Therefore, we analyzed the existing, out of our experience, our existing PLM approaches. And therefore, I want to go to the next slide. And we see digital twin should have all information, for example, to making a decision or something else, but you should have all information out of all phases. So, and this is a slide, what you see is from a work from the beginning of the 2000. And what you see here is that you integrate in the PLM activities all data from the phases into your product model. So that is one aspect we see also for the digital twin, and this is already considered in the PLM approach. The next slide, please. And then the next slide, you see on the right side for the PLM, you see a picture. It is also in the beginning of the 2000, and it shows the data flow from the real space to the virtual space, and also the information and also the process, what is coming from the virtual space to your real space. And this is our mostly definition, also understand, how to the understanding, today the understanding of the digital twin. And you can make this picture also for the digital twin. You see the data flow between the real environment and the virtual environment is already considered in the PLM activities. And on the lower side, you see the digital twin activities that you see you have to measure. So that means you need sensors to sense the real world activities and to bring this to a decision, for example, in a simulation, and to make information or a decision to the process and process optimization. That is today the understanding of digital twin. So also similarities. Next slide, please. And here it's a work out of 2009, and they worked for the product IPS, means Industry Product Service System, IPS Square, and they considered the product and the services and defined a meta model for PLM. And this meta model for PLM considered 4 aspects: the object types, the life cycle phases, the users, and the process types. And that means all information to build up really the thing in a mostly real way. So this meta model can be used to implement and to define really your digital twin. So that is just to show you there's nothing new from the scientific view on the digital twin. And please go to the last slide. And in Germany, we said that is if you have new things, but seems to be the old basics, then you can say that it's an old wine in new bottles. So there we see from our perspective the digital twin is an old wine in new bottles. But should we go further with the digital twin? Yes. And why we should do this? We have a scientific basis for out of PLM what we can use for digital twin. And to be honest, the digital twin demonstrates really the benefits for the industry. It's easier to integrate the thinking of digital twin into the industry than the PLM aspects. I'm working now around about 20 years in the PLM area, and it is very difficult to convince the industry from the real thinking of PLM. The mostly for the industry colleagues is PLM, nothing else as the PDM system. Just the PDM system is PLM, but PLM is more than the PDM system. But this understanding to implement is very difficult. But to implement the digital twin as a word and as a technology is much easier. So therefore, it makes sense to think about digital twin, but to use the existing models and strategy out of the PLM to bring digital twin also to a success. So thank you for your attention. That is all from my side. And thank you for your attention, and thank you for your invitation. And also thank you, Milan, for the session share. Thank you, Vitaly, for your invitation, and really for the good organization. I know it's very difficult to switch from really a presence conference into a digital conference. So you managed it very good. Thank you for that. And thank you for your attention.
Tak, okay. Maybe Vitaly help me some in chat.
I am monitoring questions at this moment. I didn't see any questions in the chat. I think it was a very clearly report, and that's why no questions. Thank you very much, Professor. It was really interesting for all participants, I believe.
Can I one question? Europe speak about European Digital Innovation Hub. Do you join to these activities in Duisburg?
Not now.
Not. Okay. Because we speak about it very strong, and this is interesting activities in networking for cooperation. And thank you very much.
Yeah, thank you for this information. Thank you, Milan.
Greetings to Duisburg.
Thank you. Bye.
Bye.
Bye. Thank you.
Okay, and next speaker is ready because he joined to chat, and this is a representative of University of Linköping. Alex Prod. I'm sorry because I find this name. Okay, welcome in this virtual space because I think this is very good example of globalization. Because I sit in Czech Republic, Vitaly is in Ukraine, Arun was in Germany, you joined from Sweden, and this is very good example of globalization. Okay, now you can start your presentation, and time is yours.
Alex?
Alex is not, maybe problem with microphone. We don't hear it. And several seconds ago was okay, and now is. Hello. Disconnect and connect, maybe. No. Hello?
Can you hear me now?
Yes, yes.
Okay. Thank you very much, and sorry for the trouble.
It's good.
Okay, I don't touch anything.
You can start now.
So I would like to thank you a lot for the invitation. It's a great opportunity to participate in DSMIE conference and to hear so many nice topics. They are a bit out of my scope and my area. And I hope that I can prepare my talk, open up some new possibilities and for you all. And I wish that feel free to bring up questions later on. So my area is biogas solutions, and can I have and I'm an associate and a professor at the University of Linköping, and I don't see my presentation now. Can I see it? Milan. Oh, thank you. So, and I just skipped some, and I will talk a little bit about my university and myself in the department at the end. So if you are short of time, so I will present today and talk about this the Nordic model of the biogas solutions. And this model is actually based in whole Scandinavia, the biogas sector, which is a big sector, big economic sector, and it involves with many kinds of industry. It's here you have an overall view of that. Is that you have some landfills, and then you have pre-treatments, and you have a organic matter source, and then some pre-treatments, and I don't see my presentation again. Milan. Okay, that if we can, okay, and so we have the pre-treatment and then digestion, and then you produce biogas, which can be used as for transport and as biofertilizer, and in my opinion is one of the best tools or technologies to implement the circular economy concept. Next slide, please. And when I have all these markings, is because people ask me about which are the challenges, future challenges, if that's a kind of established technology in Sweden. And my answer is all that in all this small, I don't know, in all this areas that it marked in this circles, it's just areas that we are working, and there's still a lot of space for improvement, increase in efficiency, increase of extracting valuable products or getting more energy. So these are all areas that have been focus of research or is ongoing, and you can also ask me later on question. Next one, please. And I was knowing about the limitation of the time, I decided to talk about local challenges and global challenges, and how biogas solutions could actually contribute to this local and global challenges. And then local challenges, I will talk about the example of the public transportation base here in biogas in Linköping, Sweden, the co-digestion of two different industrial sources, wastes, and because of this background of this conference, I decided to just show some brief examples of some potential energy source that we can get from waste from the industrial textile industry, for example, and then I hope that can stimulate future collaboration. Next slide, please. So in Sweden, 20 years ago, there was some, well, now more than 25 years ago, there was a concern about too much organic material in wastewater, air pollution caused by diesel buses, and there was a slaughtering waste in the region that had to be handled. And in 1995, the city decided to found a company called Technische Werken, which is a municipally owned regional energy and waste company. And it's a cooperatively owned by meat producers, the region, the municipality, and farmers organizations. And over some time, we realized that it was a win-win solution, because this waste, which was causing lots of trouble, became biogas to buses. It was able to produce a high-class certified fertilizer to the agricultural sector from the region. It added value to waste and created, actually after that, there was a creation of this market for biogas and biofertilizer. So there was no market for that, and now there is a big market around the region. Next one, please. And here the picture of the 5 buses in '98 when the program started, and 2018, 20 years after that, all buses in the city run based on biogas. And biogas that generate from the waste that, for example, I produce here in my house. I put in a green bag, it goes, it has a different pathway, you can ask me later on. But from the system perspective, they learn lessons, and is that the important for this system to work, to reach that level was, it was a long time of learning and technical development. It was a gradual improvement of specialized actors. A collaboration was very key to success. So academia, industry, municipality, government, people were collaborating a lot. The government participation, of course, they implemented the biogas chain. And there was one aspect that the companies always say, there's a clear rules and the long-term direction. It's very necessary for successful development of this kind of enterprise. Next one, please. Keep an eye on time. Another example and local example and how important it is to this cooperation between academia and the industry, it's based on the pulp and paper industry. And here you have a result of one of the papers. I'm not actually involved with that, but was done in the department. I'm working in the biogas group. And it was a project, an ordinary project in that the group evaluated the potential of producing biogas from pulp and paper industry. And there was some studies, several papers, some PhDs, but there was a potential of relatively low biogas production and was high cost. And because of the characteristics of this waste. But next one, please. But this result that was maybe not very promising in terms of business, I cannot see my, can I just, I'll talk about it, but I cannot see my. But one of the solutions, one of the Scandinavian biogas, it's a company that it's very much oriented and working with our department. And they were contacted by a paper mill industry in Norway that wanted to treat it and to decrease the amount of energy that they were investing. And so they have this paper mill waste and they don't know what to do with it. Or, okay, people don't know what to do that. And this company came with a very smart idea, was that in that area, next one please, it was the production of fish. It was an area of fish production, and I cannot see my slide. No, I don't want to. I'm looking, but I'm trying to. I will just open here, just a minute. But then, just a moment. So slide number 9. Okay. So, and the solution was, yes. So this company, what they do is just that they get from the surroundings, they get waste of fish, and then they just combine with this waste of the paper mill industry. And actually, they manage now to produce 125 gigawatt of liquefied natural gas. And this is kind of not unique example, but that's the potential and the power of this technology of biogas, because you can really turn many kinds of waste, combining the right things into energy and consume energy. Can I see the next one, please? Slide 10. Okay, so and here's just an example of current work that I'm doing, and is the effect of pretreatment on biogas production for waste from the textile industry. And I like this example because I never actually measure not even one time potential from the textile industry to evaluate the biogas potential. But based on a meta-analysis, we could see that some kind of pre-treatments can actually generate or facilitate or allow the change organic matter in a way that more biogas will be used. And if you're seeing different kind of treatments, is because different industries have, or the textile industry have been trying different things. But this kind of result, only based on literature, can really drive a lot of conclusions. And this has been one of the aspects that we've been focusing here. And just to highlight that sometimes you don't need to spend a lot of time in the lab if you just dig in the literature and find out different kind of potential that you can apply for your industry, in this case, the biogas. And next one, please. So let's see if I can see it. No. Okay. So, and given this increased biogas demand here in Sweden, to make it, I have 4 examples of that fits to agriculture or to industry, like methane emission from, for example, from manure could stop. And this is one of the major problems that the agriculture sector is, or the meat sector is facing, is because there's lots of greenhouse gas production by the cows and manure. But you could produce energy based on this waste. And you also have biorefinery slaughteries, and there is more, can be more competitive if you increase this biogas production, becoming it more, turning it more available. And this example, these 2 examples from the pulp and paper industry and the fish processing industry, actually you can combine different kinds of ways that you have really hard time to handle, and combining them and find solutions that's good for everyone. Next one, please. And coming to some examples of global challenges, I just wanted to bring up that the biogas solutions can actually contribute to almost all the 17 Sustainable Development Goals from the UN, and we are actually, how can it help to contribute to decrease the amount of human action and human activity to the planet, and scarcity of phosphorus, something that I've been especially worried for the last years. Next one, please. And I could give you examples from every one of these 17 goals, and I just want to talk, I don't want to spend more time on that, but the biogas technology can actually contribute to every one of these. If you think very careful, you can find very clear case and very clear situations. And this is one of the tools that can be applied and should be applied by all kinds of countries to achieve these Sustainable Development Goals that is a agreement by the UN. Next one, please. And one of the aspects that I like here is that in this picture you can see 2 papers. One is a Roxon paper published in Nature, showing that this group of researchers found out and made an evaluation in which aspects were actually the society exaggerating in influencing the limits of planetary limits. And at that time, 2009, the group found out that it was loss of biodiversity, excess of nutrient, and then climate change was actually the largest human threat to the planet. And in 2015, the same group, led this time by Stefan, they realized, they rearranged their evaluation, but actually still agree that the loss of genetic diversity and the excess of nitrogen phosphorus used by humans in other planets are actually a huge threat to the planet, maybe more than climate change. Next one, please. And yeah, okay. But then my question was that I just wanted to show with this slide is that actually the biogas solutions, biogas technology could be actually a solution to all of these threats to the planet. And I just highlight one example of that are here, but I would like to highlight that biosphere integrity and biogeochemical flows. And by treating waste and being able to generate energy from waste would actually, in developing countries, be a way to generate energy and somehow also decrease the amount of pressure on forest because of natural resources that would be used for energy. And of course, if you have a biogas reactor that generates energy and the leftover is a biofertilizer, you can actually decrease the amount of these flows of nutrients that we are actually putting in our planet. So all in all combined, and I could talk about all these examples. Next one, please. And this is specifically important because we don't usually talk much about it, but this curve in red is the known phosphorus reserve in the planet. And then these dots are the amount of phosphorus that we are actually using per year, exploring in the planet. And it's expected in 2150, which I know is far away from now, that our reserves will go down. But if they go down, there is no way we can produce food for so many people without phosphorus. There's no replacement. We cannot fix it from the atmosphere. And if we throw it in the way we're doing lots of waste in the planet, we will end up getting no phosphorus. And this biogas technology actually, next one please, actually allows to reuse. Next slide please. Actually allows us to reuse lots of the phosphorus, and this is one of the major threats that could be imposed to our human population, because if the phosphorus in the ocean would have a very hard time to recover it. Next one, please. So I want to, here's just a list of things that the biogas production, the biogas use, how it improves the environment by resource recycling, less ecotoxicology, acidification, purification, but next one, please. I don't think I have the time. I want to respect my time. So as a conclusion, I want to say that biogas can provide sustainable solution for local, regional, and global problems. And I dare to say that there is no sustainable future for our society that does not include biogas solution. Next one, please. And just to talk a bit more about the biogas center that I'm representing here is actually a very nice model between academia and it's called triple helix. It's between academia, municipalities, and industry. And this biogas research center is comprised of 25 researchers from basically Linköping University and SLU, which is another Swedish university. But we have partners from the biogas production distribution sector, technology providers, agriculture, or horticulture. An interesting thing is that because we actually meet and discuss several aspects related with biogas, and we work almost hand by hand. And this center is actually financed by 1/3 of the companies actually provide 1/3 of the funding. The universities provide 1/3 of the funding with the researcher time. So if I invest 40% of my time in the center, it's a very big income to the center. And the Swedish Energy Agency also contributes with 1/3 because it wants to promote this event. And next one, please. And just to shortly talk a little bit about the department that I'm working, we work with biogas and we envision the areas where we are focusing on for the next until 2030 is that we are combining and focus on basic and applied science. The research is basically many times oriented to benefit the whole society. We work with long-term vision and we are strategic motivators, so we have strategies and then we target them. And we also know that we have the potential to develop new areas like biogas solutions for hospital waste, and this kind of things, a very open area. Next one, please. And to be very specific, these are the areas which we work in. If you're interested in that, you can contact me. We work, of course, to make the biogas more efficient, more stable, more predictable. We, of course, the biogas reactors are basically based on interaction and network of microbes, and we are studying also the degradation of different kind of chemicals because the anaerobic digestion is very efficient in that, and we're working on different kind of process wastes and organic matter characterization. It's very deep research in that, and we try wet and dry digestion is a new area because of waste of space and so on. Next one, and next please. And on regional scale, I would like to highlight that these technologies are actually very efficient in storing energy that's cheap energy. For example, you have wind power and you have no consumption in the society. What happens with this energy is lost, and you don't have batteries to store it. But via using biomethanation, you can actually transform this energy into hydrogen, and you can insert it into and turn it into methane, which is easily stored and distributed. And of course, we are also studying in partnership with Sumy State University, and specifically Dr. Irina Blieva, the application of digestate in farms and other aspects. So it's work that it's going on. Next slide, please. And one of the when talking about a bit on a national level, we are also focusing on how to integrate with wastewater treatment, and specifically, and maybe people from industry interested in recovering rare earth element from digestate. And this is ongoing research. Specifically, I'm leading that, and a very promising results with different technologies, biotechnologies to recover that. And because this is one of the major problems in the lack of these elements, it will be a future problem in all scales. Next one, please. And to finalize my last slide before I thank you, this is just to say that you can actually focus on global problems by integrating data, by doing meta-analysis, and you see new patterns. And in our internationalization strategy from, I would say, at least my department, that we have been targeting two main countries like Brazil and Ukraine, and specifically Sumy State University. And the aim is really to co-develop technology and the more possible to include this business dimension and interaction and stimulate startup companies with biogas sector. And by that, I thank you, and I think I didn't exceed my time. So thank you very much for your attention. Thank you very much for the invitation. Sorry for the confusion with the headphone. And thank you, Vitaly, for inviting me. Thank you, Milan, for organizing this section. And thank you very much. I'm really pleased to having had the chance to participate in this meeting. And congratulations for the organization and how to handle everything, because with these COVID times, that's definitely not very easy. Thank you very much.
Okay.
Thank you very much, Alex.
Thank you very much, Alex, for your presentation. Vitaly, some question in chat.
At this moment, I didn't see questions. I'll check again.
Yeah. This is very interesting contribution for me. This is very good.
I could just say that I could challenge you all from this conference to present me a sector, industrial sector, and give me 5 minutes, and I can think in a way that the biogas reactors could contribute, but not now.
Okay.
Okay. Thank you.
Thank you very much to Professor Edel. Dear Milan, thank you very much for serving as session chair. Thank you very much to our keynote speakers, to Professor Nagarajan, to Professor Prast for current challenges, solve solutions and future trends about digitalization and industrial ecology, biogas, and so on. Thank you very much for your acceptance. And thank you very much for a very interesting presentation.
And thank you very much, Vitaly, for organizing an invitation and preparation this conference.
Looking forward to seeing you, all of you, in Ukraine, in Sumy State University or Kharkiv.
I will.
Yeah, I know.
If COVID allows. I was looking for.
Okay, thank you very much. We will finish this session earlier, and we can start our afternoon session at 2 p.m. by Ukrainian time.
Okay.
Bye-bye.
Thank you. Bye-bye.
Bye. Bye.
До побачення.
До свидания. Спасибо, Милан, все было классно. Молодец. Большой молодец.